Today we're going to talk about differential equations, all right? And differential equations are equations that are derivatives. That's where the differential part comes out, all right? And we want to go back and get the original function, okay? So we can do that through integration and some other things, okay? So if we have y equals 3x squared plus 6, okay, dy over dx, then that would be 6x, right? And if y equals 3x squared minus 4, dy over dx would be 6x again, right? And dy over dx for 3x squared plus 7, that would be 6x. So all of these have the same derivative, right? But the original function came from 3x squared, and the only difference between them was these constants, right? So we have to remember that if we're solving one of these differential equations, one of these, to go backwards, we're going to need to add that constant, okay? So here's our first problem, okay? So we have dy over dx is equal to cosine of 3x squared times this 15x to the fourth, okay? So dy, we know that dy over dx is equal to cosine of 3x to the fifth times, and then this 15x to the fourth. And you may want to look at this and go, wait a minute, okay? If I take the derivative of 3x to the fifth, that would give me 15x to the fourth. So we're multiplying. So this came from the product, or not the product, the chain rule, okay? So this derivative, we can tell because it's multiplication, came from taking the derivative. This came from taking the derivative of the inside function, which that's the chain rule, okay? So what we're going to do is we're going to multiply both sides by this dx. So it becomes dy is equal to cosine of 3x to the fifth times 15x to the fourth, and then dx. And what we're going to do, that's where the dx comes from in our integration, okay? It comes from moving the dx over to the other side. So in order to solve this, what we're going to do is we're going to integrate both sides. So we're going to integrate the left side. So we're going to integrate dy. And remember, this is an indefinite integral, which means antiderivative. And this is the integral of cosine of 3x to the fifth times 15x to the fourth dx. When we integrate dy, we wind up with y, okay? And we have to think, okay, so we got a derivative that's cosine, okay? So what function could we get the derivative that we would take the derivative and get cosine, and that would be sine. So this, and then this part right here is just the derivative of this. So this winds up being sine of 3x to the fifth plus, and we got to remember from up here, some constant c, okay? And this is called, there's a name for this type of solution for this differential equation, and it's called a general solution to it. So basically, this is called a general solution because I could put any value of c in here, and if I took the derivative, it would give me this one, okay? So that's why it's called a general solution, because this represents all functions whose derivative would give me the original problem, dy over dx. All right? Now we're going to talk about particular solutions, okay? So for this one, we now know that dy over dx is equal to e to the x plus 8x cubed, and y equals 0 when x equals 1. Okay, so this is the point for the function 1, 0. So what this means is we're going to be able to figure out the particular solution because we have this, it's called an initial condition, okay? We have this initial condition where x equals 1 when y equals 0, and we're going to be able to put that in and figure out what the c value is, okay? So once again, we have this dy over dx is equal to e to the x plus 8x cubed. We're going to multiply both sides of this equation by this dx, and we get dy is equal to, and I'm going to put in parentheses, e to the x plus 8x cubed dx. And then we're going to undo this by integrating both sides. So we're going to integrate dy is equal to the integral of, and this is e to the x plus 8x cubed dx. Okay, so this left-hand side becomes y. So y is equal to, okay, so what could I take the derivative of that would give me e to the x? Well, it's e to the x, because the derivative of e to the x is e to the x. So this is e to the x. And then this one is plus 8x cubed. I'm gonna have to apply the product, or not the product rule, the power rule. I keep saying the wrong rules, okay? The power rule, okay? And so we have to add, and this would be 8x to the fourth over 4 plus some c that we don't know, right? And I'm gonna clean this up. So this becomes y is equal to e to the x plus 2x to the fourth plus c. Okay, so now's where we're going to use that we know when x equals 1, y equals 0. So when x equals 1, y equals 0. That means I can do the substitution in for the x here, and the substitution for y, which is 0 right here. And so this is 0 is equal to e to the first plus 2 times 1 to the fourth plus c. So 1 to the fourth is 1 times 2 is 2. So this is e plus 2. So 0 is equal to e plus 2 plus c. Now to get my c, I'm going to move the e plus 2 over to the other side. So it becomes negative e minus 2 is equal to c. And now I'm going to have my, I'm going to be able to write my function. So it's y is equal to e to the x plus 2x to the fourth. And then we're going to add c, but adding c is the same as subtracting e minus 2. So we're going to just write minus e minus 2. And then what we have to say is, okay, what's the domain? So we have to figure out the domain for these, okay? So if you think of all these individually, like e to the x, okay, the domain is negative infinity to positive infinity for e to the x. There's no restrictions on what x could be. And same thing with 2x to the fourth. So this becomes my domain for my solution is negative infinity to positive infinity. So this graph would go everywhere between negative infinity and positive infinity. We'd see the whole graph going across on the x-axis. We would see it graphed for every x value, okay? So we're going to get into situations, which is the next example. Okay, how do you find the domain for some of these? And we're going to explain that in just the next problem, okay? So the last curve was continuous, right? And that because it was continuous, there was no breaks in the graph, that gave us the domain of negative infinity to positive infinity, okay? But when the curve is discontinuous, in other words, not continuous, there's a break, there's some problem, okay? The initial condition only gives a solution for the continuous pieces of the curve that contain the initial condition. So there's going to be breaks in the domain, right? So we have all these intervals that we could have, and I'm going to show you how to do this, okay? But you're going to have all these different intervals, but the domain can, for these differential equations, can only be one interval. So how do you pick which interval it is? Well, it's the interval that's going to contain these initial conditions, okay? All right. So here we go. Let's get started with this. All right, we're going to approach it the same way. So here we want to find the particular solutions, and we know that when x equals pi over 4, we know that y is equal to 2. So that's an input and an output. That's going to allow us to figure out what the c value is. Okay, so right off the get-go, I'm going to get dy by itself. So I'm going to multiply both sides by this dx. So that's the same. Okay, so dy is equal to parentheses 3x squared minus cosecant squared x, and then dx. And then we're going to have to integrate both sides. And integral 3x squared minus cosecant squared x dx. Okay, so the integral of dy is y. And then we'd have to apply the power rule for 3x squared. So that'd be 3x cubed over 3. And then minus cosecant squared x, right? So we have to think here, all right, what all we know is derivatives right now, right? We don't have any techniques other than, okay, the derivative of this would give me this. So what function, what trig function, because this is definitely going to come from a trig function, what trig function could I take the derivative of that would give me the cosecant squared x, okay? And so, or negative cosecant squared x, and it would be cotangent x. So this is plus cotangent x plus your constant c. Okay, so we're going to clean this up a little bit. Y is equal to x cubed plus cotangent x plus c. Once again, when I plug pi over 4 in for my x here and here, I'm going to get a y value of 2. So that means 2 is equal to pi over 4 cubed plus cotangent of pi over 4 plus a constant c. Okay, so this becomes 2 is equal to pi cubed over 4 cubed. So 4 times 4 is 16 times another 4 would give me 64 plus, okay, and then I'm going to draw a diagram for cotangent of pi over 4. So pi over 4 would be in the first quadrant. And I know my angle right here is pi over 4, which makes this side 1, and it's going to be positive 1 because I'm going up, and I'm going to the right, so that's also going to be positive 1, and the square root of 2. So cotangent, okay, so tangent is y over x. Cotangent is the reciprocal of that, so it's going to be this x over this y. So this is going to be plus 1 over 1, or 1, and then plus c. So this is 1, all right, so I'm going to move the 1 over, and I get 1 is equal to pi cubed over 64 plus your c. So you could move that over and you get 1 minus pi cubed over 64 is equal to c. That's my constant. Now you could get a common denominator of 64 over 64 and then write this as 64 minus pi cubed all over 64, and that's equal to your c. Okay, now if you write your c as this, the difference of these two, or you write c as one fraction, both are correct. So I want to make that really clear. Like it's not like you have to go all the way that I went, okay, all of this far. You could stop right here and use this c value, okay? I'm just showing you an alternative way of looking at it, okay? All right, so back up, we can write our c. So right here, this c we know is this or this, either one. So now I know that y is equal to x cubed plus cotangent x. And I'm going to go ahead and do this one. Okay, so it's going to be plus 64 minus pi cubed over 64. Okay, now there are some breaks in this. Okay, there's not a break for x cubed. It's the cotangent x is causing breaks because remember, cotangent x can be written as cosine x over sine x. So here's where the problem happens when sine x equals 0. So sine x can't be 0, right? So what angles cause sine x to be 0? So you're thinking about this, okay, what angle would cause, now remember, this is the angle, this x is the angle, and this is the ratio, right? And the sine ratio is y over r. So this would have to be, your y would have to be 0. So where is y 0? Well, it could happen right here, and it can happen right here, okay? So this x, all right, so back here, okay, what can x not be? X cannot be 0. It can't be pi, but it also can't be negative pi. So it can't be plus or minus pi. Okay, and we come back around here, like we rotate all the way around. So it also cannot be plus or minus 2 pi. Whether we rotate once this way or once this way, either way, positive or negative, right? And then plus or minus 3 pi. Okay, so I'm going to list some of these, okay, to help you understand, because this is where this is going to come in. This curve is not continuous. All right, it's not continuous because anytime x is one of these values, okay, we're going to get a vertical asymptote because it's causing this denominator to be 0. All right. So when the curve is discontinuous, the initial condition only gives a solution for the continuous piece of the curve. So I'm going to write, these are where my breaks are happening. Okay. So we would have something like this, negative 2 pi to negative pi. And there's more before this. Okay. And then union, if we were writing the domain, negative pi to 0, union 0 to positive pi, union pi to 2 pi, and so on, right? On both sides, we can continue going forever in both directions, okay? So there's all these individual breaks, right? So what we're looking at, okay, what this means up here, all right? And let's go back. The initial condition only gives a solution for the continuous piece of the curve. So this is where all the continuous pieces are, okay? The continuous piece of the curve that contains the initial condition. So these are all this is all based on your x values, right? So where is x equals pi over 4? Well, x equals pi over 4 would be right in this interval right here between 0 and pi. So that's the one interval that we're going to use to specify the domain for this differential equation, okay? So x equals pi over 4 is in that interval. So what we have now is y is equal to x cubed plus cotangent x plus 64 minus pi cubed over 64. And the domain for this function is not negative infinity to positive infinity. It's the interval that contains the initial condition. So in this case, it'd be 0 to pi. And that's it. So that's how you do this. Okay. So you got to be aware of, okay, when I do the function, and if there's any discontinuities, all right, I have to pick the one interval that has that initial condition in it. Okay. In this case, it'd be x equals pi over 4. All right. And then the next example, we have a differential equation. I'm going to show you how to solve that using the fundamental theorem of calculus. Okay. Okay, so for this next problem, I have to move this over a little bit. Okay, I'm going to zoom in a little bit too. Okay, so we want to find this particular solution to this equation. F prime of x is equal to e to the cosine x, square root of x minus 3. All right. And so if we are not able to find the antiderivative, so this is a way to do these without ever having to do the antiderivative. We can use the fundamental theorem of calculus. Okay, it's kind of like cheating a little bit. All right. And what does the fundamental theorem of calculus says? If you take the integral from a to b of f prime of x dx, then that has to equal, since this is the derivative, right? F prime is a derivative, then the antiderivative, the labeling for the antiderivative, since F prime is here, would be F, just regular old F of B minus F of A. So this is what's going to allow us to do this, because I have F prime of X is equal to e to the cosine X, square root of X minus 3. And we also know that F of 2 is equal to 7. All right. So if I start my integral at 2 and go to 7, right, or not go to 7, I know it's going to equal, I'm sorry, let me back up. If I started at 2 and I ended at x, I will come up with one of these integral functions. Okay. All right. So this is going to allow us to write, okay, if we integrate from 2 to x of f prime. Now I can't use x because that x is the input to the function, right? So, and this x is a different x. So I have to use f prime of t dt. I know this would come out to be f of x, right? We put the upper limit into the antiderivative first, and then minus f of 2. Okay. So what does that lead to? Okay. And this leads to us being able to write the function 2 to x e to the not e, I started right e times, right? E raised to the cosine of t I'm just putting t into the function here, e to the cosine of t times the square root of t minus 3, and that has to equal f of x minus f of 2. Well, what do we know is f of 2? Well, f of 2 is 7, so this is minus 7. So then this becomes the integral from 2 to x, e to the cosine of t, and you know what? I forgot to write dt right here. There should be a dt right here. E to the cosine t, square root of t minus 3 dt is equal to f of x minus 7. All I need to do is move 7 over and I'll have it. So this in turn makes f of x become an integral function from 2 to x e to the cosine of t square root of t minus 3 dt. And I have to add 7, right? So there's going to be plus 7 over here. And that's my answer. So that's what allows me to write new functions, right? An integral function, right? That would satisfy the conditions, and that would give us, if we took the derivative of this, I mean, take a look. If we took the derivative f prime of x, right? Then that would be e to the cosine x times the square root of x minus 3, and then plus 7, right? And plus 0, right? Plus 0, right? Because the derivative of 7 is 0. All right, and that's how you do these, okay? So these are called differential equations. Really, this whole next unit is all about differential equations, okay?